So to the petition of one of my viewers, I'm gonna do variational quantum linear solver, and you know who you are, Amir. So I'm kind of going ahead with my quest to kind of understand nature maybe a little bit more and really appreciate variational stuff. And so the variational quantum linear solver could be a candidate for these. I see there's an ansatz, something in here, a lot of math. Okay, let's see. Control Harmarts, interesting. What is this? Oh, a lot of code. Okay, let's just quickly start, see how far we get. So I'm not gonna play with any code right now, but I might switch to it at some point. Is this thing working well? I think it doesn't work well. I think I got it misconfigured somehow. Come on, pin. No, it's not working somehow. So okay, whatever. Give me a second. Mine probably got messed up because of I was plugging a second monitor. But anyway, so what do we do? So let me read the introduction a little bit more carefully, actually. The variational quantum simulator is variational quantum algorithm. Okay, so it utilizes VQE in order to solve systems of linear equations more efficiently than classical. Specifically, if we are given some matrix A such that A times X equals B, where B is some known vector, then VQLS algorithm is theoretically able to find a normalized X that is proportional to X, okay, which makes the above relationship true. Okay, it's normalized because it's basically what you get with quantum computing. Then I guess you'll do some classical post-processing to test, because I'm guessing those are the solutions, because if I remember well, so I guess you can express a system of linear equations like a matrix of the coefficients of your equations, and then it's multiplied by a vector of, and those are the variables in your equations, right? See if I can get that to work. Give me a second. And now since it's working, because I plugged again my second monitor. So yeah, okay. So what I meant is yeah. So what I meant is like you have. So if you have like an equation, say, for example, 2x plus 3y equals 4, and then you have like, I don't know, 5x plus 6y equals minus 7, just to say something, right? I guess what you so what A is like 2 and 3 and 5 and 6. Then you've got the vector x, y, and then you've got the sort of the force 4 minus 7. I just made up the numbers, and so the idea is okay. So and because that's basically, if you multiply that, you're doing these times these plus these times these equals these. So that's a way to represent your system of linear equations, and I'm assuming this is what it means. Now the thing is, this x in here is going to be normalized because it's what quantum computing does, and so I guess it's going to be something proportional, so it's not going to be directly x and y, right? Okay. Oops. Sorry, here I am again. I turned off the camera. Cool. Let's go ahead. Let's go ahead. So, can I just scroll down? Sorry. Okay. So, the operator is identical to that of HHL. I have never done HHL, so except probably is much more favorable computation to speed up. Okay, but this it's more NISQ friendly because it's variational. Okay, so what's the algorithm? The inputs into the are evidently the matrix A, which we have to decompose into a linear combination of unitaries with complex coefficients, where each an is some unitary and some unitary u that prepare. Okay, so you gotta decompose that somehow, but I don't know why. Then a unitary u that prepares the state B from 0, because B is known. So now recall the general structure of a variational quantum mechanics. We have a constructed quantum cost function, which can be evaluated with a low-depth parameterized quantum circuit and output to the classical optimizer. This allows us to search a parameter space for some set of parameters alpha such that blah blah is the output of our quantum circuit responding parameters. Okay, whatever. Before we actually begin constructing the cost function, let's take a look at a high-level overview. Can I just zoom this in or what? So we've got the quantum computer. I don't know what this Hadamard is doing. I don't know what. Can I paint or I cannot paint? I cannot paint because I zoomed in. If I select the painting, then I cannot zoom in unless I zoom in like this. I can't. So maybe I can open in a new tab. Oh yeah, here we go. So I don't know what this Hadamard is doing here. So this is the part that's supposed to prepare B. That's the solution of the equation. So it's not the solution. It's the stuff that's on the right side of the equality. And this is the variational part. But where is A? This is A, but what is this? What is this? I don't know. So you do something like a cost function, and then okay, so if we're not happy with it, we go back here with a new alpha parameter set, and if we're happy, okay, that's the post-processing probably to get x. But that's not classical post-processing. Okay, whatever. Let's see. Before actually begin constructing, okay, so we'll essentially we start with the QB register. Algorithm takes inputs, prepares the values, the cost function. Okay, it takes the inputs, then prepares and evaluates the cost function. Prepares and evaluates the cost function. Starting with the creation of some ansatz. If the computer cost is greater than some parameter, then the algorithm is yeah, that's what I just said. Okay, so what is the ansatz? Let's take a look at the ansatz. Let's start off by considering the ansatz, which is just a circuit that prepares some arbitrary state. This allows us to search the state space by varying some set of parameters. Anyways, the ansatz. Okay, so you just here you go. Okay, so that doesn't seem to be like QAOA where there's an actual interpretation of the ansatz. There's an actual meaning in the way you design the ansatz, or there can be. This seems to be just a bunch of rotations and control Z gates. This is called a fixed hardware ansatz. Is that a thing? Is that a thing? Is the picture called bro? Bro PNG, bro. Fixed hardware ansatz. Okay, doesn't seem to be like this is where I am. The configuration of quantum gates remains the same for each run. But unlike the QAOA ansatz, it is not composed of solely trotrized Hamiltonians, which now I know what it means, which basically means Hamiltonians that are basically you've got a cost and then you've got like the mixer, cost and mixer thing. The application of RI gates allows us to search the state space, while the control Z gates create interference between the different qubits. Okay, let's take a look at this quirk for a second. Quirk. How are we exploring this state? Can we do this? Can we do something with these? Can we do, so those are parameters. But the control Z gates are not parameterized, are they? What is parameterized in here? Homework test. That's not parameterized or what? Oh wait, parameters. Okay, the control Z gates are now parameterized. Interesting. Only the rotations are parameterized. That's funny. So if I just do like these, and what the hell? So if I try to do these, so because if these are ry rotations, I can as well just use these. It's gone. So basically, I'm gonna move those here. I'm going to use Control Z. I just want to see how the space is being explored, to be honest, because Quirk has this cool dynamic thing in here. Can I just copy that? Thought I could copy the whole column, whatever. So if I do this, it just meant no. Look at this, how it moves. And now I do these and these and these and these, and now, come on, I thought I could. Oh yeah, here you go. Copy the whole column. That should move it away. Okay, so now I got the circuit. So how does this behave? This doesn't explore everything though. Entanglement, so it does explore entanglement. I don't know. Is there a way to is there a way to visually or intuitively understand how well this explores the state? Because I guess mathematically we could take a look at the stuff, but I like the animation in here. Anyway, let's see. That hasn't really helped me with anything, but it's just what you just pick that just because. I guess there is some. I mean, there is some. A layer of rotations, and then we are. So this is a possible combination of control Zs. So qubit 0 and 1 and 2 and 0, and here there's another rotation, and then you do an, I don't know, the other combinations. I don't know why you do that this way. So it's good that it's good that it's explained. Now that it makes sense for us to consider actual cost function. Okay, so now I build a cost function. So the cost function is supposed to what is it supposed to do? How would you do that? You've got a system of equations. What do you want to minimize? I guess you want to minimize the difference to the actual solution or something like that. Or you want to minimize, maybe what you want to do, I'm just not taking, so what you probably want to do is, if the whole thing is like A times whatever, right, and that's your state, and that's supposed to be equal to B, you probably want to minimize the difference between these two parts of the equality. But I have no idea how you do that. But it's probably all classical stuff. I don't swear in these videos. How much? lies. Oh yeah, okay. So how much these lies along whatever this is, phi along B. We then subtract these from another number to get the desired low number. Then the inner product is graded. So we've prepared our state with the answers. Now we have two values to calculate in order to evaluate the cost function, namely these and these. Why? So the goal of the algorithm will be to minimize costs. So when, okay, so phi, that's what I said. So when phi is these, it's very close to B, we want our cost functions output to be very small. When the vectors are close to being orthogonal, why orthogonal? I guess this mathematically speaking, the most different you can get, right? We want the cost function to be very large. So we introduce the projection Hamiltonian. Okay. So I guess you're projecting against B. Here we have okay, I'm not going to read this. No, the second term is how much from a number to get the zero number, blah, 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 blah. So we have prepared the state with the answers. Now we have two values to calculate in order to evaluate the cost function, namely these and these. I don't know, I guess you take that from that. Luckily, a nifty little quantum subroutine called the Hadamard test. What is Hadamard test? What is the Hadamard test? Allows us to do this. Essentially, if we have some unitary u and some state, and we want to find the expectation value of u with respect to the state, we can then run the following circuit. Isn't that what I'm doing with my quantum counting thingy? Isn't that what I'm doing with my quantum counting thingy? Workspace. Quantum counting. Come on, look at this. I invented the Hadamard test. Oh man, so my okay, so my idea for better quantum counting is the Hadamard test, because that's it, right? Okay. For me, the intuition behind this, and sorry for this, but it's quantum counting. So the idea is, if this is Grover algorithm, right? Like that's going to give you a distribution of whatever, and then the numbers you're looking for. And so obviously, what this intuitively means is, for when your qubit 0 is like 0, you don't do Grover. If it's 1, you do Grover. Which kind of means if you don't do Grover, you just have the equal superposition, right? Here, so you just have the superposition. If you do Grover, you're gonna have elements that so you're gonna have elements that have how is that? So you're gonna have elements. Let's put it this way: you're gonna have more. For some reason, so let's say you're looking for the number 001. So this number is gonna be upper, right? It's gonna have like a high amplitude. So this means you're gonna be measuring these more often. Somehow that correlates. it's got to correlate. Just trying to think intuitively, but I think that's the idea. I trust it kind of correlates with the. So it's literally correlating with the amount of because then it means that it's one. So so the amount of this number, the amount of times you measure the qubit on depends on the number of elements that you have in here. Because if you would have the equal superposition, they would have like 50-50, right? But because it's because you don't have it, you have some elements. Yeah, okay, because you have more elements, right? That kind of stick out. This means that this really happens more often than the equal superposition, because you have like an equals, like if you've got like your two possible outcomes like out of this initial state, and these are all like these, right? And then here you've got like one element that's like these. So that basically means that that's gonna happen more often, something like this. I don't know, but yeah. So, but that's it. So, what is this really? So, what was the Hadamard test? Allows you to do this. It doesn't you in your expectation value of u. You can evaluate the following circuit, and the probability of measuring the first qubit to be 0. So the probability of measuring the first qubit to be 0 is equal to a half of whatever this is, the real part of the expectation value, and the probability of measuring 1 is a half of the real value minus. Okay, so this I don't follow, but so there is a mathematical. So there's a way to compute that correlation or that relationship. Likely, the matrices will be dealing with when we test this are not completely real. So the real part is the actual expectation value, because the expectation value is what you want to calculate in here, right? It's one of the things you want to calculate for your cost function in here. We're gonna skip this. We're gonna skip these. 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 Hadamard test. So this is the Hadamard test. Apply the fixed ansatz to the circuit, and then Synthesis begins computing every possible term using the Hadamard test. The recurrence is to prepare a state, and then perform controlled operations with some control and accuracy in return matrices. So basically, okay, so basically, because, what am I doing? Because, so this is the Hadamard test here. How is that? How is that? You're essentially, so you're essentially calculating, you're essentially extracting some representation of the phase, correct? You're essentially doing, so if I quirk, so what you're essentially doing is, if I do a so let's do a Y rotation like these, okay, and another Y rotation like that. So my elements have all a phase of 90 degrees. And what happens if I do these now? So 50-50. Intuitively speaking, expectation value is. Whatever that is. So what are you doing? So you're just calculating the phase. Like I want to try to find the first of all, what's special about this algorithm, and second of all, whether there's any logic to this or whether there's any intuition to this that could, if those are fourth rotations, right? So you get these. So essentially, what if I change this to that? I don't know what I'm doing, to be honest. Trying to understand what is these reading really. What is these here reading? It's somehow reading something that correlates with the with the expectation value, right? So if we have yeah, it's interesting. So it correlates with the expectation value somehow. If we it's a hardmark test. Okay, so if we have these, right? What is the expectation value of these? It's sort of the average of those values. That's what you would say, right? Of like, let's do that. Calc. Rechner in German. So it's 62%. Do I gotta do all these? Let's do 2 qubit. Let's do these easier. So 70% 0, right? Or the expectation value. So I think I've got a 2 with a -1 and +1 because it's a Z observable, right? So I should do what? So Miha is going to help me with these. Nasty Thoughts has a. I'll only remember these because of this article. Expectation value. So 0, the eigenvalue of 0 is 1 if 1 if -1. Okay. This one, no. Oh, but those are then different eigenvalues here. Every 0 with a 1 and every 1 with a -1. Okay, but that's just 1 qubit. Right. So in this case, I don't know how to calculate the expectation value, to be honest. I guess it should be the average value, right? That's what I remember. So if it's 0, 1, 2, and 3, I remember that somewhere. So if it's so this would be like what 12.5 times 1. Can I get scientific. So I do 12.5 times 1 plus, come on, 2. Okay, so 12.5 times 1 plus 12.5 times 2 plus 2.1 times 3. I think that was my, and the 0.1 we ignore. 43.8. Eh. What is that? Sorry, people. I'm so stupid. You're probably wondering why you're watching me. It's 1, bro. The average. So how would I do this now? So if I would say that these control Z, these. How is that related 1? I don't know. I don't know if I calculate that correctly, but it's got to be somehow related to the expectation value. Because the point is, the intuition behind this is that, so as you get through here, you have to imagine, no. It's like phase estimation, isn't it, right? So you're applying the Z gate. I've lost all that intuition. Okay, but this is something to dig into. And again, I want to do this intuitively and not just like go through the maths, through the math that's in here. But you do that, and what happens next? So, this information will be solved. Actually, sorry, I'm only concerned with the gate Z and I. What? It's also important to know that for the purpose of the implementation, the systems of equations will actually be solving. We are only concerned with the gates Z and I and identity, so I only include support for these gates. The code includes number identifiers. That's the application of different gates. 0 for I and 1 for Z. Blah, blah, blah. So there is a sophisticated way to solve of solving for these values using a newly proposed subroutine called the Hadamard overlap test. Man, that's a lot of new stuff in here. That's a Hadamard overload test, overlap test. Hadamard test, Hadamard. Okay, it doesn't seem like there's something new in here. Come on. A C-sided paper at the end or what? Okay. Something to explore. But for this tutorial, we'll just be using a standard Hadamard test where we control each matrix. Use extra qubit when okay, control fixed ansatz. So what are we doing here? What the hell is this? Creates a control ansatz for calculating these stuff in here with a Hadamard test. I don't like the way this is explained, but it kind of makes it interesting at the same time. So this Hadamard test is something that I smell can be useful to learn what it's really doing. And it is somehow related to quantum counting, to the stuff that I've been exploring. So, but here, the only thing they do is they control like that. So is this just, why are they controlling with an extra Z in here? And why this qubit? So I might want to take a look at, it's somehow got to do with the expectation value, right? And my sense tells me, again, my intuition tells me that this is all about the following. So if you, which is kind of, again, I'm kind of going to repeat a bit what I already explained with quantum Grover, with quantum counting, right? But so if we think about, this part of the circuit, like you're getting in here and now you're like in the 0+1 state, right? So if it's 0, and let's think classically. If it's 0, it means we're not applying U. So we're staying with like whatever this is, right? But if it's 1, what we're doing is we're staying with these. So we're staying with this world, right? Now, in the case of Grover's algorithm, what was easy to understand. So what is it that it's testing against? So it's applying a Z gate. So what effect does this have if I apply a Z gate here versus a non-Z gate? The trick here will be that, so this Q is off, is I apply a Hadamard gate is like these. So what happens with these and like that? Can I move this whole column here, right? So the only thing this is doing should probably just replace those by a concrete rotation. Will make it easier for me to understand because everything is moving too fast. Seems to evolve together. And, okay, I gotta understand that a bit more. What I was explaining, I forgot. Yeah, so you kind of have the two worlds, right? In Grover, in the quantum counting world, so you have the, it's not here, it was here. Yeah, so you have these, and so intuitively, the expectation value of these or the percentage of times is going to measure 1 sort of tells you something about you, because that's what kind of makes different, right? So the question is, what does it tell about you, right? And that depends on what's going on with the qubits. In the case this U is Grover's algorithm, well, here you just will have an equal superposition, but here you're going to have an equal superposition, and for example, say 2 elements, you're looking for 2 elements, right? So as these elements grow, as the more elements you have, the more you're going to measure 1. So there's a direct correlation between the percentage of times. So when you measure here, the amount of times you get 1 and the amount of elements you have. And that's what I'm playing with when I say better quantum counting, because this basically means that if you take the whole system into consideration, right, you're gonna end up here more often than in here. Yeah. Now, I guess you can generalize these as in like, that's kind of what it really means at the end of the day, is that it tells you something about the expectation value. Because whatever you do, it's going to kind of tell you the difference, right? Yeah, maybe that's something with expectation value. I got to revisit that. That's okay. That's been actually helpful. It's give me some extra clues in there, I think. So for some reason you do these. I don't know. This is still black magic to me. So the create a circuit for you, and our implementation will pick you as, yeah, that's great. Why not? Let's just pick something else. Come on. It's a bunch of control automates. Why is that you? Okay, I think I'll just go to the paper. I'll just do the paper probably. Why? Why is this speaking? Like, can't we just start with an example? So we're calculating some stuff. We're using an ansatz that nobody tells you why. Special Hadamard test. Control fix ansatz. Cost function. So here you summarize all your beautiful thing. And yeah, this code may look a bit daunting, whatever. The final step is to actually use this code to solve a real linear system. Well, first look at the okay, so it's a beautiful linear system. So what is these? So this is 0.45. Copilla is the optimized method. Yeah, okay. Whatever. Okay, whatever. Whatever. So where's the paper? Well, thanks for the citations at the end. Oh no, yeah, acknowledgements. No. Research paper, variational quantum. So, but what is it? What is it that's like variational about it? To be honest, okay. So this is the paper. When was this paper published? Is this such a wow? So that was like September 2019. That's such a recent paper. That's cool. I have to admit, though. Where's the so? But it's VQE, right? I mean, what is? So it's just VQE with a fancy ansatz, is it? Isn't just VQE? I mean, you prepare an ansatz, you measure stuff, and then life goes on. But there's something different in that. But what does it finally measure? I mean, this is what I don't understand. So what is it? What is it that it's finally measured? So the actual circuit, circ H, and select this control fix ansatz, control B. So this is the ansatz, and then there's a control B. Okay, cost function. where's the yeah, sorry, the bro. Hey bro. Let's be say f of a. I don't know. So what does the paper look like? 16 pages. Oh, here you go. The whole thing here. Results VQLS overview. Cost functions. Cost evaluation. It's really theoretical ansatz. Heuristic scaling. Training algorithm. That's going to be a nice one to crack. Implementation of quantum hardware. Discussion. Oh, we got some circuits in here. That's nice. Okay, so I got some circuits in here. That is actually nice. Circuit for the Harmar test is to compute the coefficients and calculate the inner product. I think the trick is focusing on what this Harmar test is doing. I think that's the trick. That's the key. Sorry. Okay, so here you really see some of the inner, like at least laid out the way that the high level one seems to lay down. Okay, so I see you've got the ansatz. Fixed structure hardware efficient ansatz is used to solve the linear systems introduced in section B1. Since A and B are real, it contains only RY rotations. Okay, so there's an actual reasoning. Okay, so since A and B are real, we're only doing RY rotation gates and control Z gates. So we're not using RX, which would take us, okay, that's the reason. That makes more sense. So what this is saying is someone should just do like a Bloch Sphere visualization tool that it's like a quirk, but just a Bloch Sphere in here. But what this means is so if you have the Bloch Sphere here, that's X, that's Z, and that's Y, and so we only want to move across this plane. It's beautiful. So we only do Y rotations. Okay. So we're not willing to explore the complex side of the whole thing. That makes intuitively sense. The dressed CNOT is composed of CNOT preceded. Okay. The control gates are supposedly for interference perspective purposes, but yeah, but the whole point is like intuitively, what is these ansatz representing? Just randomly, just a space of stuff, just a space of. So you just like try and error, like you're just brute forcing through the space. Then you're calculating something out of that element, so you can calculate your cost function. Okay, so that's, I think, so you just define a space that is constrained to explore the stuff that makes sense for your, just for the fact that you're solving real number equation systems. Okay, I'll definitely crack this one intuitively. I'll try to explain that intuitively at some point. I'm okay. I'm gonna stick to that until I figure it out. I promise you, no distractions with other stuff. But the Hadamard test, that's an interesting. It's funny that I see this here because it's the correlation that I've been talking about here. It's so here there's an actual It seems like a simple explanation. Okay, I'll leave it here because I think it's quite late. Yeah, I think it's about time I leave it here. These intuitively, I have to think about these. What does these mean? The problem is that you see, the thing is that this is designed this way because in the paper it's more generic, right? They do this control thing. They do an actual control operation. And so that's what's not clear to me. So I want to try to understand that a bit more from the paper, maybe, but maybe I'll search for, is there anywhere else VQLS? Explain anywhere else. Penny Lane. Oh, Penny Lane. My dear friend Penny Lane. So there's an actual, oh, nice. Okay, so we'll do that next time. Channel setup, circuits, variational part, Hadamard test, local cost function, variational optimization. Yeah, that seems like a nicer. Oh, so there's an actual quantum solution, comparison, quantum probabilities. Cool. So we'll go through this one in the next video. That seems to make a bit more sense. Or that seems to be a bit better explained. Let's see. Problem, linear solver, first method, second method, simple example. Cool. Stay tuned for more stuff.